Okay, so here we are in quiz number 6. It says find the area of the shaded region. I want to find this area. Okay, so this is a standard normal distribution. A bell curve is a normal curve or normal distribution. Same thing. Bell curve, normal distribution, same thing. So it's a big bell, right? See how this is a big bell shape? Call that a normal distribution. How do we find it? Well, it's going to be on our TI calculator, and I've got the instructions right here. This is again the exam number 2 notes, which for the online students is on my Canvas course shell, and for my students in class I'll pass it out or email it to you. So use the exam number 2 notes to help you out. Here, this is step 4 in the exam number 2 notes. Basically, it says when you get something normally distributed and a mean and a standard deviation are given. Is that us? Yeah, it's a normal distribution. Mean 0, standard deviation 1. What do? First, draw a normal bell-shaped curve. Well, we've already got one. And put the line in the middle with the mean below it. So I'm going to put the line in the middle with the mean below it. 0 is the mean. Put that right in the middle. Okay, then what? When they ask for a percentage, they're asking for the area of the shaded. Let me give you that there. They're asking for the area of the shaded region. That's a percentage. So they want the percentage. They want what portion of the bell curve is, what portion of the bell curve is shaded? What percentage of the bell curve is shaded? Is that like 80%? It looks like more than half, right? Because from here to here, this is half, and it's more than half. So I don't know, maybe 70%, 80%, 90%, something like that is shaded, right? They want to know the percent. So when they ask for the percent, n equals 1. Don't worry about that. If they don't say, then n is 1. Later, they'll give us a specific n, and then we'll do this type where it's more than 1. They'll let you know when it's more than 1. Otherwise, if they don't say anything, it's just n equals 1. We'll talk more about that in a minute. Now they're saying, what do? You do normal CDF, left, right, mean, standard. That's your TI calculator. So you got to go again to second distribution, and when you do, you got to go down and choose normal CDF. So it's another one of these probability distributions like the binomial was, but this one is a normal cumulative distribution function. So bell shape, a normal distribution. It's how things are normally distributed. Bell curve, normal cumulative distribution function. So like a binomial, but a normal. And left edge, right edge. What else did it say? Left, right, mean, standard. Mean, standard. So normal CDF. What's the left? Now, what do they mean by left edge, right edge? They mean the left edge of the shading and the right edge of the shading. Well, the left edge is the negative 1.18. The right edge, this is infinity, right? Because it goes, it looks like it stops here, but really it just gets really, really tiny going right forever. It stops here. This is the left edge for sure, but it goes to the right forever. But you can't type infinity into your calculator, so how do you put in infinity? Put in like 5 or 6 nines. That's like infinity. So left edge, right edge, mean, what's the mean? 0. And standard deviation, 1. There we go. Hit the buttons on your calculator. You'll get 0.8810. That's the answer to number 1. Now on number 2, they're changing up the game a little bit. They're giving you the percent up here, or the decimal, same thing. They're giving you the area, and this is what they're asking for. They're reversing it. See how they gave you the z, which is the numbers on the bottom of the curve, on the last problem, on number 1, and asked you for the percent. But now they're giving you the percent and asking you for the z. Well, that's right here. When they give you the percent already, it's inverse norm. So that's again on your TI. You choose second distribution. And then inverse norm. So it's an inverse normal distribution. They're asking you an opposite question, an inverse question. And how does it work? Area to the left, mean standard. Area to the left, mean standard. That's why it's important to have these exam 2 notes with you when you take exam 2. These will really help you. Area to the left, mean and standard. All right, let's do it. Inverse norm. Area to the left. To the left of what? Well, here's our spot. What is the area to the left? It's this area. Well, I don't know what that is. It's not even shaded. Right. So here's what we got to do. This part is shaded, and it's 0.8289. So then this part is 1 minus 0.8289, which is 0.1711. How did I come up with that? Well, that's like rain and no rain. If the chance of rain is 0.8289, then the opposite is 1 minus it. So the area to the left is 0.1711. Do you see that? Do you see how that works? So when you use the inverse norm function, you've got to find the area to the left of your spot, of the spot you're looking for down here. So the area to the left, this area, is the opposite of the area to the right. So the area to the right is 0.8289, then the area to the left is 1 minus that. Just like if there's an 80% chance of rain, then there's a 20% chance it won't rain. Or in decimals, I could do, if there's a 0.80 chance of rain, there's a 0.20 chance it won't rain. Or vice versa, right? It's 1 minus. Got to do 1 minus. Okay. So, and then mean, what's the mean? They told us the mean, didn't they? Yeah, mean 0, standard deviation 1. So 0, 1. Hit the buttons on your calculator, you'll get minus 0.95. That's what that z value is. Does it surprise you it's negative? It makes sense because here's the middle. Here's 0. So this, positive numbers over here. This is a negative 0.95. That spot. It's not a probability. It's not an area. It's a number on like a number line at the bottom of the graph there. This is like a number line, and this is 0. This number is left of 0, so it's got to be negative. 0.95 rounded to 2 places. Okay, let's take a look. So assume that a randomly selected subject is given a bone density test. Bone density test scores are normally distributed, meaning they're bell curve distributed. Mean of 0, standard deviation of 1. Draw a graph and find P7, the 7th percentile. This is the bone density score separating the bottom 7% from the top 93%. Remember what percentile means? We learned that in the first unit of the course. So the P7, 7th percentile, means 7% below. If you score at the 7th percentile bone density, that means 7% of the whole population is below you, has lower bone density than you. The rest of the people, 93%, have higher. You're pretty low in bone density. So which graph shows that? See how it's right there, right? This looks like 0.07, a really small percentage to the left. See how they graded the shading? The shading here is very small, like 7%. And we got to find that. We got to find that P7. So how do we find numbers on the bottom? Well, when they give you a percent, they're giving me the percent. They're giving me the 7%, aren't they? The 0.07 decimal. They're giving me that part already. So when they give you a percent, it's inverse norm. So I'm going to do inverse Norm and area, left, mean, and standard, right? So what's the area to the left of this spot? Well, it's just 0.07. We don't have to do the 1 minus this time like we did last time. Why? Because last time they gave me the area to the right. And so to get the area to the left, I had to go 1 minus. But this time they're just straight out giving me the area to the left. See, it's to the left. The shading is to the left there. They're just straight out giving me left. So just grab it. And then the mean is, what is the mean? Oh, mean 0, standard deviation 1. And hit the buttons on your calculator, and you'll get negative 1.48. There we go. All right, here on number 4. Assume that adults have IQ scores that are normally distributed with a mean of 104.8, standard deviation of 18.6. Find the probability that a randomly selected adult has an IQ score greater than 141.6. Hint, draw a graph. Okay. So all these questions we're going to draw a bell curve because they said IQ scores are normally distributed. They are. IQ scores are normally distributed. Always put the middle and put right there what is the middle. It's the mean, 104.8. That's the middle of the bell curve of IQ scores. Okay, and then where do we go from there? Where's the score 141.6? That's going to be way up here, somewhere to the right. How did I know to go to the right? That's bigger. 141.6 is bigger than the middle, bigger than the mean of 104.8. And they want IQ scores greater than 141.6. Where are greater numbers? To the right or to the left? To the right, huh? This is greater to the right. So they want me to find the shading, the percent to the right of 141.6, don't they? So remember how we do this? Getting back to the thing here. When they ask for percent, that's what they're doing. They're asking for percent. Normal CDF, left, right, mean, standard. So I'm going to go normal, CDF, left, right, mean, standard. So normal CDF. What? So left and right of what? Left and right edges of the chunk of shading. So this is the left edge of the shading. Now the right edge goes forever. So the right edge is infinity, but you know we go 9, 9, 9, 9, 9, a bunch of 9s, right? So left edge, 141.6. Right edge, 9, 9, 9, 9, 9. 5 or 6 9s. Mean, what's the mean? The mean is the middle. This is the mean, right? Mean is the middle, the average. 104.8. And the standard deviation, they told me somewhere there's 18.6. All right, hit the buttons on your calculator, and you will get the answer, 0.0239. That's a 2% chance. So if you grab somebody at random, I'll put it up here, 0.0239. That means if you grab somebody at random, the chance their IQ score is going to be greater than 141.6 is only a 2%. 2.39% chance. Very few people have an IQ score that high because the middle is the 104.8, and so very few have an IQ score higher than 141.6. Okay, number 5. Suppose that sitting back to knee length, like if somebody sits in a chair, they measure how far from their back to their knee when you're sitting down in a chair. For a group has a normal distribution with mean 23.3 inches and standard deviation 1.1. All right, so you got a group of people, their average, their mean, the length when they're sitting down from their back to their knees is a little over 23 inches, and the standard deviation, which is the average distance from the middle, telling you how spread out that data is, 1.1 inches. These data are often used in the design of different seats, including aircraft seats, train seats, theater seats, and classroom seats, right? Because they want seats that'll fit the average person. Instead of using 0.05 for identifying significant values, use the criteria that a value x is significantly high if the probability of that or greater is less than or equal to 0.01, and the value is significantly low if it's less than or equal to 0.01. Find the back-to-knee length separating significant values from those that are not significant. Use these criteria as a back-to-knee length of 2.5 inches significantly high. Okay. Using these criteria. All right. So here we go. So they want back-to-knee lengths greater than blank and less than blank are not significant, and values outside that range are significant. All right, what in the world are we talking about? This is a confusing one, huh? So basically, how are you supposed to see this question, let's say, on exam number 2? You're definitely going to see a question like this on exam number 2. What words are going to jump out at you? Normal distribution, give you mean, give you standard. All right, let's go back. And what do they want? So, what are you supposed to do? You're supposed to draw a bell curve, aren't you? Every time you get normal distribution, you draw a bell curve. So let's draw a bell curve. Here's my bell curve. Put in the middle the mean. What's the mean? 23.3. Okay. And then they, what do they say? Probability that at some spot or greater is less than 1%. That's a percent, right? 0.01, that's a decimal. And that means it's x or greater is 0.01. And this is x or less. This is some other x value less, that's 0.01. Okay. So what are we talking about? So basically, that's the curve they're describing. They're saying find the top 1% and the bottom 1% of back-to-knee lengths, for people. So basically, they're going to make chairs for theaters and aircrafts and trains and things, classrooms, that fit everybody except the top 1% and the bottom 1%. People that have the, average, it's going to be made to fit all average people that have the average back-to-knee length, except for the top 1%, and the bottom 1%. People with really long upper legs, I guess that is, and very short upper legs are not going to fit in the seats, but everybody else will. That's how they design seats. They use statistics to figure out, because, they want it to fit a lot of people, and so they figure the percentage of people they're going to fit with the chair. They're going to rule out, because you can't make a chair that'll fit everybody in the world, because some people are really big, some people are really small, and it just won't work. But you want to have a chair that fits a great percentage of the people to be useful for general population. So what do? You statistically do a bell curve, because people's everything pretty much that occurs naturally is normally distributed, bell curve. We got a middle, and they're asking me to find the value x that is significantly high, meaning the probability that you're there or higher is top 1%, and significantly low, bottom 1%. Okay, so I got to find that. So how do you do it? Well, notice they're giving me the percentage. Let's go back here. When they give you the percentage already, it's going to be inverse normal. Area left, mean, standard. Okay, so they're giving me it already, so I'm going to go inverse norm, area left, mean, standard. Now, okay, so it's inverse norm, area left. So how much area is to the left? Now that's a little tricky. We can find it right here. What's the area to the left? 0.01. So let's just find that x value by saying the area to the left is 0.01 Don't worry about by the way, these are the same. See how they're both x? This one's going to be negative. This one's going to be positive. Well, I'm sorry, I'm sorry. I'm not doing a very good job. They're not going to be the same. I'm getting confused. Let me try again. But we're doing well. So far, so good. We're going to find this x first. The area to the left of that spot is 0.01. And that's the area to the left. The mean is 23.3. That's the middle. And the standard deviation, 1.1. So hit the buttons on your calculator, and you'll get 20.7. So this is 20.7. That's that x value right there. I'll just write right here. This is 20.7. And now, how are we going to find the higher one? This one right here. Well, same thing. Inverse norm, area left, mean, standard deviation. So area left. So if you're right here, what's the area to the left of you? Well, it's all this, including this down here and all of that. Well, how much area is to the left? Well, how much area is to the right? 1%. So how much is to the left? 1 minus 0.01, which you know is 0.99. 99% of the area is to the left, right? This is the upper 1%. So only 1% of all people are at this length or higher, so 99% of people are below. So the area to the left is 99%. The mean is still the same, 23. I can't write that 3 there. 23.3. And the standard deviation is 1.1. Hit the buttons on your calculator, and you will get 25.9. That's what this spot right here must be. 25.9. So in other words, if you want to go from the lowest 1% and the highest 1% back to knee lengths, it goes from 20.7 to 25.9, the middle being 23.3. That'll give you the lowest 1% and the highest 1% of all people as far as back to knee length when they're sitting. So greater than 20.7, less than 25.9. And so a back to knee length of, what about 25.5 then? Where's 25.5? Well, 25 point, they're just grabbing a particular value now, 25.5, and saying, hey, where's that? Is that like in the middle, or is that like in the extreme high 1% or extreme low 1%? Well, 25.5 is about right there. It's not quite to 25.9. So it's not in the extreme high spot. So it is not significantly high because it is inside the main curve. It's inside the range of values that are not considered significant. It's between here and here, the middle section that's not considered significantly high or low. So there we go. So whenever we want to find spots on the bottom of the curve, and they give us the percentages to begin with, this tells us do inverse norm, area left, mean, standard. So area to the left of this spot was 1%. Area to the left of this spot was 99% because it only had 1% to the right. Had to use 99. Had to use 01 there. Got my two answers. There they are. Okay, number 6. Survey found that women's heights are normally distributed with mean 63.1, standard deviation 3.2. The survey also found that men's heights are normally distributed with mean average 69.7, standard deviation 3.7. Most of the live characters employed at an amusement park, those live characters walking around, Mickey Mouse, Donald Duck, have height requirements, minimum 55 inches, max 64. Okay. Basically, we're going to conclude that most of those characters are women because of how short they are. They must be statistically, usually, typically women. There's not normally that many men that short. That's what we're going to find out. Find the percentage of men meeting the height requirement. What does the result suggest about the genders? It suggests they're not men. All right, let's find it. So what are we going to do? We're talking about a normal curve. So here we go again. I'm going to draw a normal curve. And put the middle on. What's the middle? We're doing min. This is a min curve. For min, what did it say about min? Min's height, mean 69.7. So I put 69.7. Standard deviation 3.7. Okay, and then they're saying, what are the two numbers? 55 inches and 55 and 64. So where are those numbers? 55 is like here, and 64 is like there. And they want to know the percentage between 55 and 64. Do you see that? Both those numbers are below the average man's height. They're saying that the characters that walk around at the amusement parks, their height requirement is between 55 inches and 64 inches, both below the middle height for men, 69.7. So the question is, what percentage, right? Find the percentage of men who are in that category. So that's what they're asking us. What's the percentage of men between those two heights? Well, how do you find a percentage? Let's go back to the notes. When they ask for percent, normal CDF, left, right, mean, standard. Right? So I'm going to go, okay. Let me squeeze it in over here. So normal CDF, left, right, mean, standard. So normal CDF, left edge. What's the left edge of the shading? 55, that's the left edge. What's the right edge of the shading? 64. Mean, 69.7. Standard deviation, somewhere. Min, standard deviation for min, 3.7. Hit the buttons on your calculator, and you'll get 0.0617, which changed to a percentage becomes 6.17%. Since most men do not meet, right? Only 6% of men are between 55 inches and 64 inches, which is the height requirement for the live characters at the amusement parks. So only 6% of men fit that. So since most men do not meet the height requirement, it is likely that most of the characters are women, They're probably women. Only 6% of men could fit in that height range. Now, if the height requirements are changed to exclude only the tallest 50% of men and the shortest 5% of men, what are the new height requirements? Okay, so another bell curve. Whoops. Let's draw ourselves another bell curve. Okay, I'll put the middle on. We're talking men again. This is the men curve. I don't even know why they gave us the women data. The mean for men is 69.7. And they're saying if the height requirements are changed to exclude only the tallest 50% and the shortest, so the tallest, that's 50%, right? That's in the middle. I mean, 50% is in the middle, tallest 50%. Why it went to the right? Because it's the taller people, right? The taller people going this way, the shorter, right? Because this is a number line down here. Here's 69.7. That's the average men's height. You know, taller men, 72 inches. That'd be 6 feet, you know, and then men over 6 feet, and all the NBA basketball players over here, right? Get the idea? Going to the right, you know a number line. To the right, the numbers get bigger, like 80, 90. They get bigger to the right, and they get smaller to the left. So the taller men are to the right. It's saying the tallest 50%. So that'd be the half of the curve to the right. And the shortest 5%. So that would be down here, a bottom shortest 5%. So they're giving me the percentages right there. And here, I'll make this a decimal. 0.50. They're giving me the percentages. Let's go back. when they give you the percentage already, inverse norm, area left, mean, standard. Area left, mean, standard. So inverse norm, area left, mean, standard. Okay, so inverse norm. So for this spot right here, got to find these two spots. For this spot right here, the area to the left is just 0.05. That one's easy. The mean, what's the mean for mini and 69.7? The standard is 3.7. Hit the buttons on your calculator. You'll get a 63.6. Now let's find this spot. Oh, we got this spot. That's 69.7. Yeah. So this is 63.6, 69.7. That's the two spots on the curve, right? Because this is the middle, because it's got 50% of the curve to the right. The tallest 50% are to the right of the middle. We already have the middle, 69.7. So the new height requirements are a minimum of 63.6 and a max of 69.7. So that's the new height requirements on part B. Okay, the overhead reach distance of adult females are normally distributed with mean 195 centimeters, standard deviation 7.8 centimeters. Find the probability that an individual distance is greater than 208.4. 208.4. Okay, let's draw ourselves a bell curve. We'll draw a bell curve like usual. Put the middle on like we always do. What's the middle? The mean? 195. Okay. Now we're saying greater than. Now it's greater than 208.4. Where's 208? Well, it's somewhere to the right. 208.4 is certainly bigger than 195. It's to the right. Now, it says find the probability greater than. Greater. I'm going to shade greater. Where is greater than 208? Is greater to the right or to the left? Greater is always to the right. Right? Greater numbers, bigger numbers are to the right. Lesser numbers are to the left on every number line, right? The positive numbers, bigger numbers go to the right, smaller numbers go to the left. Okay, so it says find the probability. In other words, find the percent up here. That's what they want. So what are we going to do? Let's go back. When they ask for percent and n is 1, normal CDF left, right, mean, standard. So I'm going to go normal CDF left, right, mean, standard. So, like usual, that's going to be normal CDF. What's the left edge of the shading? 208.4. What's the right edge? This is left edge, right edge. Remember, we're always taking the left edge and right edge of the chunk of shading. The left edge of this chunk of shading is 208.4. The right edge is infinity, goes forever to the right, so we just go 9, like 5 nines. The mean comes next, mean, and then standard deviation. What is the mean? 195, comma, standard deviation, 7.8. There we go. Hit the buttons on the calculator. Get 0.0429. That's the answer here. 0.0429. That's part A. Now, part B is very similar, slightly different. Check it out. It says find the probability that the mean for 15 selected distances is greater than 192.8. That's 15. We're talking about 15 people now. The last part A was an individual. So N was 1. It was one person in part A. But now in part B, we're talking about 15 people. not one person. We're talking about the average for 15 people. So we're saying, what's the chance of that? Well, what's going to change on that? Let me get a fresh screen here. Okay, so we're doing the mean for 15 people. Let's draw the bell curve again. Middle is still 195. And greater than 192.8. Where's 192.8? Just a little bit to the left. 192.8 is a little smaller than 195. But we want, which side, here's the 192.8. We're going to shade either the right side of it or the left side of it. What does it say? Greater than. Where's the greater stuff, right or left? It's to the right. We're going to shade everything greater than 192.8. Here's the greater stuff, right? Greater than 192.8. But it's for n equals 15. They want those are saying you're not just going to grab one person and say, hey, what's the chance they're greater than 192.8? We're doing something harder. We're saying we're grabbing 15 people, and we want to know what the chance is that the average of the 15 people is greater than 192.8. Well, let's go back to our notes, our exam 2 notes. We're talking about this case now. N is more than 1 for a group. It's normal CDF again, left, right, mean, standard, but there you got to divide by the square root of n. That's the only difference between this formula and that formula. When n is more than 1. Okay, let's do it. So I'm going to write normal CDF, left edge, right edge, mean, standard deviation divided by the square root of n. So it's going to be normal CDF. Left edge of the shade, there's the left edge, 192.8. Let me get this out of the way. So this is the left edge. What's the right edge? It's infinity, or a bunch of nines. Right, make that 5 nines. Whoops, comma. So left edge, right edge. What's the mean? 195. What's the standard deviation? They told us the standard deviation. 7.8. Divided by the square root of n. So you have to hit the square root button on your calculator just like that, divided by the square root of 15. Close the parentheses, hit the buttons on your calculator. You're going to get 0.8627. 0.8627. There we go, 0.8627. Now it says choose the correct answer below about what? This question. Why can the normal distribution be used in part B, even though the sample size does not exceed 30? Yeah, we had a rule. If you pay close attention to the lecture notes, I'm not sure everybody did that. That's okay. It said basically you can only assume things are bell curved, if either two ways. If the original original curve is a bell curve, is normally distributed, then anytime you grab a group, it will be. Or even if the original is not, if you grab groups bigger than 30, that'll work. See, our answer is C here. The normal distribution can be used because the original population is normally. Right here it says that the original is normally distributed. I know it's probably confusing. Honestly, I'm not going to test you really closely on that question. It's just saying, when can you assume that data is bell-shaped? The original data, it said right there, it was normally distributed. So everything's normally distributed, no matter how many in a group. Okay, so it says, assume that females have pulse rates that are normally distributed, mean this, standard deviation that Then 1 adult female, 16 adult females. In other words, it's just like the last problem. They're giving us a question with n equals 1 and here with n equals 16. So we'll have to divide by the square root of 16. All right, so you know how to draw a bell curve. Put the middle on. What's the middle? The mean, 73. And then they're saying between 67 and 79. Now, where are those? Where's 67 and 79? 67 is somewhere here, smaller, and 79 is somewhere there. So they want us to find the area between those two. The probability. Probability is percentage. Remember, PP, probability percent. They want the percent. So when they want percent, what do you use? When they ask for percent, they want percent. It's normal CDF. So it's going to be normal CDF, left edge, right edge, mean, standard deviation. Normal CDF, left edge, this is the left edge right here. Left edge, this is the right edge right here. 67, 79. The mean is the number in the middle, 73. Standard deviation, they told me, there is 12 point, I can't see that, is it 12.5? Yeah, 12.5. Put that in, hit the buttons on your calculator for 8a, and you'll get 0.3688. And then part B is exactly the same question. It even says 16 and 79, except it's for 16 people. So I go normal CDF, 67, 79, the left edge, the right edge, the mean. Whoops, I'm supposed to write mean, but put in the number. 73 is the mean. Now, what do you do for standard deviation when there's a n equals 16? It says right here, when n is more than 1, divide by the square root of n. For normal CDF, but you divide by the square root of n. So take the 12.5, same number, but divide by square root 16, close parentheses, hit equals, get 0.9451, like that. Down here, why can the normal distribution be used? Again, since the original population has normal distribution. This is one of these, the original is normal, so when you take a group of 16, right, if the original population, females, have pulse rates that are normally distributed, then even if you grab a group of 16 of them, it's still going to be normally distributed. There's a rule that says even if the original population is not normally distributed, if you're grabbing groups bigger than 30, that it'll make the new graph become a bell curve. So it's kind of nice, even if the original data is not a bell curve. Ours was right here. They said the original data is a bell curve. So for sure, since the original is a bell curve, we don't even have to think about it. But if the original was not a bell curve, the groups, so when you take groups of size 30, groups of 30 or more, 30 or more, make a bell. They make the data become bell, even if it wasn't originally. That's what they're getting at. Okay, number 9, sample data for the arrival times and mins, blah, 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 blah. Here's a bunch of data. I don't need to read all those words. Bunch of data, blah, 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 blah. Is it normally distributed? I mean, if we took all this data and put it on a graph, would it kind of go like this? Would it be bell curved or not? How do you take a whole bunch of numbers? We don't want to graph them by hand. We're going to do it on our TI calculator and find out if it's bell curved. There's actually 2 different kinds of graphs that the TI can make to figure this out. So let's go take a look at what those graphs are. Here's the instructions. Again, I'm on the exam 2 notes. which are on the Canvas course for online students, or I'll email it to you, hand it out for the students in class. All right, it's number 5. Checking if a list of data is normally distributed. Put the data in L1. So that's the first thing. Put all this in L1. That's very tedious, right? Go to Stat. Here we go. Go to Stat and Edit and Enter and put all that data in L1. That's step 1. Hit Second Stat Plot. Enter. Put the cursor over on and hit Enter. Okay. And then, so once you've got that going, now move down to Type and move the cursor to the 3rd graph. We'll just do that for now. In a minute we'll do the 6th graph, but the 3rd graph. So go down to type the 3rd graph. So there's going to be, when I say the 3rd graph, what I mean is, let me show you. You'll see when you go to Second Stat Plot, hit Enter, put the cursor over on, hit Enter, move down to Type, and you'll see these 6 graphs. 1, 2, 3. There's little graphs here. 4, 5, 6. I mean this one. This 3rd graph, which it kind of shows some bars, is what it does, like this. So choose that graph, this graph right here. Move the cursor there. And then as soon as you do, actually, one more thing. I want to stick in one extra bit of instructions. I'll call it C again. Do something else for me. Hit the Y equals button without hitting second. Just hit Y equals. And if you'll see the list like Y1 equals, Y2 equals, if any of those cursors, equal signs are highlighted, you need to turn them off. So if any equals are highlighted, that means it's going to try to graph those old equations also, and we don't want it to, because it's going to, instead we want to do the statistics graph. If any equal signs are highlighted, then move cursor on them and hit Enter. That'll turn them off. It's like a light switch, just off, on, off, on. Just move your cursor onto the equal sign, hit Enter, and it'll turn it off. Just make sure they're turn all equal signs unhighlighted. Turn them off. Turn them all off. Okay, then go on to step Z. Just hit Zoom, which is the very top row in the middle, and then hit 9. And what it'll do when you hit Zoom and 9 is it'll do a stat graph. So this for this data. And here's what you'll get. Here's what I got when I did it on my calculator. Let me show you. Here's the axis system. I got a graph that looked like this. I had a box up here, and a box here, and a box about like that, and then one like that, and then over on the right I had 2 of them over here. That's what it looked like. Does that look like a bell? No, it's not very bell. Especially because of these over here, these are called outliers, meaning they're parts of the data far away from the rest of the data. This almost looked bell in here, but then these outliers are kind of ruining it. So it doesn't look all that bell. So that's why we say it's not bell. And so that's answer A. No, because the histogram of the data is not bell-shaped. There is more than one outlier. Yeah, you can't have 2. See how this is 1 and 2 little bars out there. You can have one outlier, but having more than one, like 2, just means it's not, that data is not really bell-shaped. It's bell with a couple outliers, and that means it's not bell, really. And then not only that, there's one more way to test. Let me give you the second way. I mean, that's good enough. That tells us it's not truly bell. This group of data is not truly normally distributed. It's not bell-shaped. But then there's a second way. The points in the normal quantile plot. Now, how do you get that? That is, if you go back to what we typed out here, the normal quantile plot, that's the 6th graph right here. So again, if you go to second stat plot, enter, move down to type, and now move over to the 6th graph. That's the one, it shows like some kind of line thing like that. Go over to that one, move over, just keep pushing the right arrow, till you get to the 6th graph, and hit enter to highlight the 6th graph, and then just hit zoom and 9. You don't need to turn off the y equals anymore. It's already been turned off. Just hit zoom and 9. And what you want to get, what I got when I did that, is a graph. Let me try to show you my graph. I got a graph that sort of looked like, oops, kind of like this, and then up here there was like dots up there. So the question is that in a straight line? No, not really. It's kind of curved a little bit. Plus, you've also got these outliers. You know, these 2 data points. So the points in the normal quantile plot do not lie reasonably close to a straight line. Yeah, that's called a normal quantile plot, and it's supposed to be a straight line. It's if it is a line, then data is bell, or normally distributed. Yeah, so it's kind of weird, huh? You want this normal quantile plot to come out, it needs to come out like a straight line, or really close to a straight line. If it comes out to be a straight line, if the normal quantile plot comes out to be a line, then that means the data is bell-shaped. This data is really bell-shaped. Or if you just graph the original data like this, it should look like a bell with maybe at most 1 outlier, but this had 2. So there we go. Okay, so number 10, a random sample of male systolic blood pressures is given below. So let's go to that. Here it is. So here's the numbers. You know the deal. Put into L1. So put that data into L1. That's pretty time consuming. Put it all in. Once you've got it in, here we're going to do which of the following is the normal quantile plot? So remember those instructions. Here it is. For the normal, so you got to be on the 6th graph for the normal quantile plot. So go through these steps right here. Put the data in L1. Go to second stat plot. Hit enter. Put the cursor over on. Hit enter. Move down to type. Move to the, no, not the 3rd graph. We're going to go to the 6th graph because we want to, this one right here, the 6th graph, because we want a normal quantile plot. And then hit zoom and 9. And what you'll get is this data right there. And so what does that look like? It looks pretty much like a straight line, doesn't it? Those dots are really close to a straight line. So we'll say yes. Does it appear to be from a normal distribution, a bell curve? Does it come from a bell curve? Yeah, the normal quantile plot, if it's in a straight line, then yes, because the pattern of the points in the normal quantile plot is reasonably close to a straight line. So again, the steps for figuring that out are back here. These are the steps for graphing either a bell curve, which is the third graph, or a normal quantile plot, which is the sixth graph. You get those by putting data into L1, choosing second stat plot, which is the upper left-hand corner, hit enter, put the cursor over the on, hit enter, move down to type, and go pick your graph, either your third graph for a bell curve, or the sixth graph for a normal quantile plot, hit enter, and then hit zoom and 9, and you get your graph. So there we go.